All right, hello all physical science students. I wanted to go through and make a video today talking about work and power, but before I get to that, I wanted to make sure that you all know that I am missing you dearly, and I do actually hope that we can come back to school sometime this year. If that happens, great, I'm looking forward to it. If it does not, that's okay, I'll see you again next year, and I look forward to that as well. So, just want to let you know I'm thinking of all you guys. I'm trying to help you out with these videos. Hopefully they are helpful. Again, if you have any questions, shoot me an email. I will be checking that regularly to try and help you out as much as I possibly can. So we are going to go through a couple work and power calculations for this video. This is going to be your second assignment in your packet. That is from, this is the second packet, so this is March 30th. The week of March 30th is where this packet is coming from. So hopefully you already have this packet, and this is going to be your second assignment over work and power calculations. Before we do any examples on here, I want to give you kind of one example that is not on here. And the example I have here is, this is my spring packet that I have picked up from the school. And let's say, a little bit of a thought experiment here, let's say that I pick up this packet and I know that this packet is going to have a force or a weight of about 2.5 newtons. Let's say that this packet weighs about 2.5 newtons, and we will include that up here. And we're going to say that at 2.5 right there. And we're going to say that I am also going to take this packet about 4,800 meters, or about 3 miles to my house. Let's say my house is about 3 miles from here. So we're going to take it about 4,800 meters to my house. So that is going to be our distance here in this problem. Meters. So we are actually going to be using this formula up here for work. So remember, work equals force times distance. And we said that work in our notes realistically is just the transfer of energy that occurs when a force is applied to an object and it makes that object move. So if you apply a force to an object, so for instance, if the packet's just sitting on the table and I pick that packet up, I have applied a force to that object that has made the packet move. And if I calculate the distance from the tabletop to this, or if I measure the distance, I can figure out how much work or how much really energy has been done here. So that is really what we're doing in this problem here. We're saying that you're going to pick up your packet, it's going to weigh 2.5 newtons, and we're going to take it 4,800 meters back home. If we'll say that home is about 4.8 kilometers or 4,800 meters away. Now there's a couple key things we got to keep in mind here, that this is not a perfect example in that we're going to have to assume that you kept the packet at about the same height. So when you picked up the packet, let's say you picked it up off a tabletop that's about 1 meter high, and you did not move it from 1 meter high all the way home. So you walked like this. You walked the whole packet, you kept it about as 1 meter high the whole time, you sat down in the car, and you still kept the packet at the same height. So it's not a perfect example, but we're going to assume that you didn't lift the packet or lower it at all, because that would throw off our calculations. So to solve this problem, we basically are going to calculate work, and don't forget, work is measured in joules, because realistically it is kind of a little bit of a measure of energy. So we measure all energy in this class in joules. So to set up this problem, you would basically read through it, but in this case there's no problem that you have to read through. So make sure you read through it though, and then you would define your variables. So in this case, I already know that the force or the weight of the packet is 2.5, distance 4,800 meters. So what we're going to do next is we're going to plug back into this equation of work equals force times distance. So we will just set it up here where our work will equal a force of 2.5 multiplied by a distance of 4,800. And all you have to do is plug that into your calculator, and you should get a nice whole number of the work equaling 12,000 joules. So the work from taking this packet from the school back to my house or your house, if you want to think of the example that way, the work done would be about 12,000 joules of energy that was needed to get that packet from the school back to your house or my house, wherever it may be going. So that's just a little bit of an example right here. But moving on to an example that is actually in your packet, we're going to do number 5. That is at the bottom of the page here for work and power calculations. Number 5 at the bottom here. And number 5 is going to state that a 5 kilogram rock is lifted 2 meters. So in this case, I have a little bit of a quartz geode here, so we'll assume this is our rock. And let's say that it's on the ground, and then I lift it 2 meters up into the air. So that's really what's happening here. And we'll assume that this is much heavier. Obviously, this is not a 5 kilogram rock. This is much lighter than that. 5 kilograms, that's around 12 pounds. So this is obviously much lighter than that, but we'll assume that for this example. So we have a 5 kilogram rock. It is lifted 2 meters. and you need to find the amount of work done. So we are looking for work in this problem, and we are given a couple variables. So the very first thing we should do next is define what variables I already give you. So we know that our M, or our mass, is going to be 5 kilograms for this rock. So we will write 5 kilograms there. We also know that the rock is lifted 2 meters. So that is going to be our distance there. If you lift it 2 meters, that will be your distance, or D here, so 2 meters. Now we need to figure out how we can get to the next step here. And if you look at number 5, I do give you a bit of a hint. I do say that you need to use force, to find force, you have to use F equals ma. Remember Newton's second law of motion, force equals mass times acceleration. The reason we need to use that is because if we look back to our work formula, you need to know the force, and we can't figure out the force without using that formula, because that's our next step here. So you need to make sure that you use F equals ma for this. We know that a is the acceleration, that's that magic number. That magic number due to gravity on Earth, it's always this number if you are standing on Earth's surface, and that is 9.81. 9.81 meters per second squared is the acceleration due to gravity on Earth. And now we don't know these two values yet, but that's what we're going to get. So right now, I will actually just leave this as a question mark, because that is actually, that's a bad question mark. But this is overall what we are looking for. We are trying to figure out what work is. So what we got to do first, though, is figure out the force. So we can use F equals ma. So I'll set it up over here. I have F, which I don't know yet, but I'll calculate. F is going to equal a mass of 5 multiplied by an acceleration of 9.81. And when you do that, you should get a number somewhere around, you can round it a little bit if you have to. It should be about 49 newtons. So our force should be 49 newtons. So essentially, that is actually going to be the weight of the rock on Earth. Now remember, weight can be measured in pounds, but for this class we are going to be measuring weight in newtons. So we have 49 newtons here. Once we have our force of 49 newtons, we can actually use that to figure out the work that is being done, because remember, work equals force multiplied by distance. So now all we got to do, and not a bad idea to maybe update that over here, 49 newtons. All we got to do next is say that work is going to equal the force, which we now know is 49, multiplied by the distance of 2 meters, because we lifted the rock 2 meters into the air. So now we have 49 times 2, and your final answer for work done for this one should be 98 joules. 98 joules for this problem. So again, this is number 5 on your work and power calculations. This is assignment 2 in your weekly packet. All right, so in part 2 of this video, we are actually going to do a power problem, and this is going to be number 6. This is on the back of your second assignment, the work and power calculations. So we're going to do a power example, and in number 6, it is going to say how much power is used if a force of 35 newtons is used to push a box 10 meters in 5 seconds. So remember that work is basically just the transfer of energy that occurs anytime a force is applied to an object and that object moves. So for example, I have a Rubik's Cube right here. I pick up the Rubik's Cube from the tabletop, and I'm going to create a little bit of work. So it's just a measure of energy that was really needed to pick up this Rubik's Cube. Now power is essentially the rate at which work is done, or basically how much work is done over a given time. It's very similar to speed, where speed is basically how far you traveled in a certain amount of time. Power is just how much work was done in a certain amount of time. So for this problem, we need to go through and read it, which we just did, and then we need to define our variables, what is already given to you. So we know in this problem that we have a force of 35 newtons. So it is not a bad idea to label our force as 35 newtons. We also know that we're going to push the box about 10 meters, so we have a distance of 10 meters. And it's only going to take us 5 seconds to push that box 10 meters. So we have everything that we need here so far that's written down. The next thing you got to ask yourself is, well, how do I figure out power? And if you think back, or you look at your notes, or you look up here, we know that power is calculated by the work divided by the time. It's actually just like the speed formula, where you had distance divided by time, but now we have work divided by time. So basically the change in energy divided by how long it took you to change that energy, basically. So realistically, it's just a rate here. So we have power equals work divided by time. So we have to figure out what work is going to be, and we don't know that value yet. So that is probably the first thing you should figure out. So we will use our work formula, work equals force times distance, and we'll just plug in the values that we already know. So we're looking for work, so we know W equals, we know that F is 35 newtons because we know that is the force that is applied to the box here in example number 6, or problem number 6. So we know that we have a force of 35, and it is going to be multiplied by a distance of 10 meters because that's how far you push the box. So realistically for this, 35 times 10, we should get that our work is going to be 350 joules. That's how much energy was needed to push this box 10 meters. So 350 joules there. Nice part is we can fill that into our variables now, and we know that the work is 350 joules. Now we have everything we need to figure out what the power used in this problem is. So basically, we'll take P equals W divided by T, or work divided by time. So we'll set it up here. P equals 350, because that was our work that we just calculated, divided by a time of 5 seconds to push the box. And if you do this, if you do 350 divided by 5, plug that into your calculator, you should get that power equals, messed up there a little bit, equals 70, and no naked numbers in this class. What are the units of power? They are measured in watts. You might have heard of watts before. Watts is what is usually on light bulbs, so you might have a 40-watt light bulb, or watts are also how we measure basically energy consumption. So if your parents get the electric bill, if you're ever curious, they might show it to you. You'll notice that electricity is measured in kilowatt hours. So basically how much energy was used. So kilowatts is 1,000 watts is really how we measure energy here, or power consumption. So in this problem, your units will be watts. You can write out watts as W-A-T-T-S, or you could just write a capital W. And don't confuse this W, this is not work, this just stands for watts now, and that is the unit of power. So that is example, or problem number 6. Hopefully this helped you out a little bit as well, and email me with any questions.